Okay, section 6.2 is an extension of everything we did in 6.1, which is the inner product concept. So now we're going to extend, just like we did for the dot product, we're going to extend the angle and orthogonality of vectors, as well as the Cauchy-Swatch inequality as it relates to the inner product. Right, so recall that the Cauchy-Swatch inequality said that if you've got two vectors in Rn, u and v, then you can go and work out the dot product, and the dot product, which is a number, if it's a real number and you take the absolute value of that, it's at most the norm of u multiplied by the norm of v. So that was with regards to the dot product. And recall that the dot product was just the product of the components that you then at the end added up. And remember that the norm was just the square root of the sum of the squares of the components. Now it turns out that we can actually extend this idea to inner products in general. Now remember we said that the dot product is a special case of an inner product. So we can go and generalize this idea to include not only dot products but inner products in general. Okay, so if we look at this representation here, so we've got two vectors u and v, and we've got the vector v minus u. Now, and theta represents the angle between the two vectors. Then recall that the triangle formula for the cosine of the angle gives us the following. Okay, so the square of the norm of that vector is the same as the square of the norm of that vector plus the square of the norm of that vector minus 2 times the norm of the vector u times the norm of the vector v times the cosine of the angle between the two vectors u and v. Okay, so from there we can go and solve for that quantity there, and we solve it as that term there. Now remember how we define the norm. The norm is defined as in terms of the inner product. Okay, then the norm of u squared is pretty much the inner product of the vector u with itself. So we can go and do that replacement. The norm of v squared is the inner product of v with itself, and the norm of v minus u squared is the inner product of v minus u with itself. Right, so applying the axioms of the inner product, we know that we can express this inner product as pretty much the inner product of v with v minus u, and the inner product of minus u with v minus u. And that we know we can take that sign out to get that term there. Right, so that is an application of one of the axioms. And then we can go and further reduce this by applying the theorem we derived using the axioms. So we can replace that whole, those two terms with. All right, so we can go and replace this term with that term there, the inner product of v with itself, plus the inner product of v with minus u, and that vector and that number we can replace with minus the inner product of v with u. Right, so now we can go and replace this term with that term there. Okay, and that is the inner product of u with v minus that, and together with minus the inner product of u with minus u. And that then becomes plus the inner product of u with itself. Okay, now we can then from this see that real number cancels with that real number. That real number cancels with that real number. And we are pretty much then left with a half times 2 times the inner product of u with v. Now remember, the inner product of v with u is the same as the inner product of u with v. That's an axiom. That was one of the axioms, right? So we can do that replacement, and that whole term there is then pretty much equal to the inner product of u with v. Right, so therefore from there we said that is the inner product of u with v. And so from there we can go and we can deduce that the inner product of u with v is this term here. Okay, now just a note, from there you can also say that because this is true, we have that the absolute value of that is the same as the absolute value of that, and because the norm is always positive, it means that the absolute value of it's going to be the same as the norm of u multiplied by the norm of v multiplied by the absolute value of cos theta. And the largest that can become is the norm of u multiplied by the norm of v. Okay, so that is known as the Cauchy-Swatch inequality for the inner product. So just like we could do this for the dot product, we can do it in general for the inner product. Okay, so we have a formula for the angle between two vectors as it relates to the inner product, and we have the Cauchy-Schwarz inequality in general. So it doesn't really matter how you define your inner product. The same results are pretty much still true in general for inner products. As long as the product you define satisfies your axioms of an inner product, this will always be true. Okay, so that brings us to Theorem 2, which is the Cauchy-Schwarz inequality, which we just derived. If u and v are vectors in a real inner product space V, then the absolute value of the inner product of u with v is at most the norm of u multiplied by the norm of v. Now you also have these alternative forms of the Cauchy-Schwarz inequality, which is that the square of the inner product of u with v is at most the inner product of u with itself multiplied by the inner product of v with itself. And I mean, that is pretty straightforward, because if you take this term here and you square on both sides, you get the inner product of u with v squared is at most the norm of u squared. And by section 6.1, the norm of u squared can be replaced with the inner product of u in itself multiplied by the inner product of v with itself. Okay, and right, the second one, the second form again just follows from that. Right, then the again the Cauchy-Schwarz inequality implies that we have this inequality here, and again it's because the absolute value of the inner product of u with itself we said is at most the norm of u multiplied by the norm of v. Then by the absolute value property we have that the inner product of u with v is at most the norm of u multiplied by the norm of v, and that thing there is at most is at least negative the norm of u, the norm of v. Okay, and basically that then means that dividing on both sides with the norm of u multiplied by the norm of v, provided that the norm, neither the norm of u nor the norm of v is equal to 0, you get then that the inner product of u v divided by the norm of u multiplied by the norm of v is at most 1 between -1. Okay, so this example here, let P2 be the inner product space with the evaluation inner product at the points x0 equals 0, x1 equals 1, and x2 equals 2. All right, and recall that this evaluation inner product works as follows. You evaluate P in the point 0 and Q in the point 0, and you multiply them together. You evaluate P in the point 1 and Q in the point 1 and multiply them together, and then same for P2 and Q2, and then you add it all together. That's how that inner product works. Now they just ask us to find the cosine of the angle between the function P and Q. So to do that, we need to go and first evaluate P and Q, the inner product, and then we need to divide that by the norm of P and Q, the product of the norm between the two, and that will be the cosine of the angle. Right, so evaluating P in the point 0, 1, and 2 respectively, we get those three values there. Then we're going to do the same for Q. And then we can easily go and determine the inner product of P with Q. And that is going to be the product of -1 with 2, plus the product of -4 with 3, plus the product of -3 with -2. And that is going to be that whole thing there. Alright, now having done that, we need to just find the norm of P and the norm of Q respectively. The norm of P is the square root of the inner product of P with itself. And that is going to be the square root of how does the inner product work. You take P, you evaluate it in the point 0, and you multiply that with P in the point 0, plus you evaluate P in the point 1 and multiply that with the evaluation of P in the point 1. And then you take P in the evaluate P in the point 2, and you multiply that with P in the point 2. And that, once you've done that, you get, and then throwing that all together, we get the square root of 26. Now we can do the same for the norm of Q. The norm of Q is pretty much going to be the square root of the vector Q's inner product with itself, and that is going to be the square root of the inner product of Q with itself. So you're going to evaluate Q in the point 0, and then you're going to multiply that with Q in the point 0. Then you're going to evaluate Q in the point 1 and multiply that with Q in the point 1. And then you're going to evaluate Q in the point 2 and multiply that with Q in the point 2. Right, and throwing all that together, So there we get our result for the norm of Q. Okay, so basically the cosine of the angle theta between these two vectors is pretty much going to be the it's going to be the inner product of P with Q divided by the norm of P multiplied by the norm of Q. Right, so we worked out the norm of Q as the square root of 17. The norm of P we worked out as the square root of 26. Okay, and going back, we worked out the norm of the internal, or the inner product between P and Q as -8. Okay, so that is in fact the cosine of the angle between the two vectors. Right, so the next we have the example. Let U be two vectors in R3, and then what they do is they ask us to find the cosine of the angle between U and V in R3, given that the inner we're working with the inner product space, where the inner product is generated by the matrix. Okay, so now remember how we defined this inner product. We defined it a specific way, and we are going to consider this problem using that defined inner product. Now recall that we defined that inner product as it's the matrix A multiplied by U, and then you take that column vector and you take the dot product of that column vector with this column vector there. Okay, so working that out, we get pretty much two column vectors. Right, so we get this matrix. Right, and then we're going to basically multiply that with U, which in this case is the vector, it's that column vector, and then you take the dot product of the next column vector. And how do you get that column vector? You get it by, right, you take that and you pretty much multiply it with the other vector V. And the vector V, we have that is the vector 1, -2, 2. So that is going to be the dot product between two column vectors. It's going to be the column vector 1, 4, and 0. The next one is going to be the column vector 1, -4, 2. Okay, and so the dot product between those two vectors is going to be pretty much 1 times 1 plus 4 times -4 plus 0 times 2, and that is going to be, okay, so now what we need to do is we need to find the expressions for the norm of U and the norm of V respectively. So the norm of U, we know by definition, that is going to be the square root of the inner product of U with itself. Okay, now the inner product was defined as the matrix A multiplied by this vector here, and then you take the dot product of that with the vector U. Right, so essentially what that means is you take the dot product between these two vectors and you take the square root of that, which is pretty much, it is this vector here multiplied by that vector there, or dot product I mean, and you take the square root of that. Okay, and that is the square root of the and so that is the square root of 17. Okay, so the norm of u is going to be square root of 17. Now we just need to find the norm of v. So the norm of v is going to be, again, it is going to be the inner product of v with itself. And that is going to be the defined inner product, dot product between those two vectors. Okay, and that we know is, it is going to be the dot product between that vector and that vector, and then the square root of that whole thing, and that's going to be, okay, it's going to be that dot product okay, and then you can go and calculate that again quite easily, and so you get that the norm of v is going to be the square root of the dot product between those two vectors, which is square root of 21. Right, recall that the norm of u, we worked it out as square root of 17, and the inner product of u with v, we worked that out as minus 15. So throwing all that together, we get that the cosine of theta is therefore going to be minus 15 divided by the square root of 17 multiplied by the square root of 21. Okay, so those are two problems that just illustrate that depending on what your inner product is defined as, that's going to influence the way that your norm, or it's going to influence how you calculate your norm. Right, next up we've got triangular inequalities. So just like the dot product, just like for the dot product, we can also derive the same inequalities for the inner product in general. And the triangle inequality holds for inner product spaces in general. So you still have that the norm satisfies this inequality here. And you also have that the distance, according to your inner product, also satisfies the distance inequality. So the distance between u and v is at most the distance between u and w plus the distance between w and v. Now we can quickly go and look at how this works. Right, if we take the norm of the vector u plus v and we square it, then that's the same as the inner product of u plus v with itself. Now using the theorems and the axioms that we had for the inner product, this sum inner product, it can be broken up into these four parts. Right, so first of all, this we can write as the inner product of u with u plus v plus the inner product of v with u plus v. Okay, and then this term we can go and split that up into the inner product of u with itself plus the inner product of u with v. And this we can go and split up as the inner product of v with u plus the inner product of v with itself. And remember, we can do that because we derived a theorem as well as the axiom we used as well to break up the inner product of vectors that are expressed as a sum between two different vectors. Right, so that then you can go and replace that with pretty much the norm of u squared plus twice the inner product of u with v, because the inner product of u with v is the same as the inner product of v with u. And that was that other axiom we had previously again. Now, that you can go and replace with an inequality. And this the inequality is the square of the norm of u plus twice the absolute value of u and v, because the inner product of u and v could possibly be negative, right? So we have that inequality holds. Right, now we said that by the Cauchy-Swatch inequality, this part here is basically I just need to delete that equality and replace it with another inequality. So that is the norm of u multiplied by the norm of v plus the norm of v squared. And that is pretty much equal to the norm of u plus the norm of v squared. Okay, and therefore your inequality then follows from there. Okay, so the norm of that we said is the norm of u plus the norm of v. Okay, this is a norm is always positive, and that's a sum between two positive numbers. So you can take the square root on both sides without having sign problems. So therefore your norm is at most the norm of u plus the norm of v. Now, the distance formula works the same, because if you have the distance between the vector u and v, that we know is the norm of u minus v, according to section 6.1. But that is also equal to it's equal to the norm of u minus w, where w is another vector, plus w minus v. Okay, and by the triangle inequality, that's at most the norm between u minus w plus the norm between w and v, and that you can replace with the distance between u and w plus the distance between w and v. Okay, and that follows from the triangle inequality. Right, next we've got orthogonality. When are two vectors orthogonal? They're orthogonal whenever their inner product is equal to 0, just like with a dot product. So as an example here, if you look at the space M22, the inner product space, where the inner product space is defined by the inner product given by the trace of the matrix U transpose V. Now the question is A orthogonal to B? So what you need to do there is you need to calculate, well, you need to basically take the inner product of the matrix or the vector A with B and see what you get there. Now we know that's the trace. That is the trace of the pretty much of A's transpose. Okay, that you then go and multiply with that vector there. Okay, now the trace, we're actually only interested in the diagonal entries, so I'm not going to work that whole thing out. So basically you've got the first row multiplied with the first column, so that's minus 2 minus 3, which is minus 5, right? So you work out whatever you have there, and you work out whatever you have there, and then you take the second row and the second column, so that's 3 plus 4, which is 7, okay? And the trace of that is clearly equals to 2, which is not 0, okay? So that is going to imply that A and B are not orthogonal, okay? Okay, so this just, again, the inner product, the dot product is just a special, it's just a special case. The dot product is just a special case of an inner product. You can define the inner product in many different ways as long as it satisfies the axioms of an inner product. So the definitions still stay the same. What changes is the way that you calculate the product. And so orthogonality still means the same. It's just going to pretty much depend on how you calculate the inner product. Okay, and theorem 4, the generalized theorem of Pythagoras. Pythagoras still works the same. If you've got u and v, if u and v are orthogonal vectors in an inner product space, then the square of u plus v, the norm of u plus v, is the same as the norm of u squared plus the norm of v squared. All right, and again that it follows from this little formula here. Remember, we said that the square of u plus v's norm, that becomes the square of that norm is pretty much the inner product of u plus v with the inner product of u plus v. And splitting that up, again like we did, it yields this little result, and then we can replace the inner product of u with v. We can replace that with the norm of u multiply the norm of v cos theta, and because the two vectors are orthogonal to one another, the cosine of the angle is going to be 0, and therefore we can replace that with equality. Okay, so Pythagoras also works with inner products in general. And then we can also extend it to the definitions of the orthogonal complement. So if W is a subspace of an inner product space V, then the set of all vectors in V that are orthogonal to every vector in W, that is called the orthogonal complement of W, and it's denoted by that symbol there. So the orthogonal complement of W is just all vectors that are orthogonal to every single vector in W. And again, just as an example, if you've got P2 and you define the inner product on P2 by pretty much it's the integral from -1 to 1 of that function multiplied by that function. Now if we let W be the space spanned by the vector x, then we are just asked to show that x squared is in the orthogonal complement. So all you need to do there is what is the span of x is just all linear combinations of x, so it's all scalar multiples of x. So you just need to pretty much show that x squared is orthogonal to any scalar multiple of x. Right, let's see x be an element in the span of x. Right, then let's look at the inner product of this vector with x squared. remember just so that you remember this, we define W as the span of x. So we want to show that x squared is orthogonal to every vector in W. Okay, so it must be orthogonal to any arbitrary scalar multiple of x. Right, so by definition, right, that's the integral from -1 to 1 of the function cx multiplied by x squared. And so that is the integral from -1 to 1 of cx cubed. And that's a simple integral to work out. Right, working that integral out, we get that that's a quarter cx to the 4 plus d, where d is an integration constant. And then basically you can go and work that out, and you'll get the following. So that is pretty much going to be a quarter c14 plus d minus quarter c minus 1 to the power of 4 plus d. Okay, and pretty much that term cancels that term there. That term cancels that term there. So you've got a 0 there. Okay. Right, so therefore that is going to imply that basically x squared is definitely in the orthogonal complement of W, because it's orthogonal to every vector in the span of x. Okay, next we have the theorem on orthogonal complements. If W is a subspace of an inner product space V, then the orthogonal complement is a subspace of V. We did prove this in chapter 4, so I refer you back to that. The subspace of the inner product space V. The inner product space V is also as a vector space. So you've got your normal addition and scalar multiplication operations, and the axioms for the inner product. Again, if you've got a vector u and v, and you take a scalar multiple of u, is that going to be in the orthogonal complement of W? Well, if let's say if W is in capital W, and if the vector u is in the orthogonal complement, then if you take the scalar multiple of u and you take the inner product of the scalar multiple of u with W, then again that by definition is that, and because u is in the orthogonal complement W, the inner product is going to be 0. Okay, so it's clearly any scalar multiple of a vector that's in the orthogonal complement of W will also be in the orthogonal complement of W. And also if you take the sum between two vectors, where both these vectors is in orthogonal complement of W, then if you take the inner product, by definition or by the axiom, that's going to be the inner product of U with W plus the inner product of V with W, and they are both equal to 0 because U and V are both orthogonal to W. So again, it's a subspace. Okay, now the next property is the one that says the intersection of W with its orthogonal complement is the zero vector. Okay, so if you look at if you take a vector y and you let this vector be in the intersection between W and W's orthogonal complement, that's going to imply that y is going to be in W, and y is also going to be in the orthogonal complement of W. But what does this mean? It means that y is in W and y is in the orthogonal complement of W. So this means that if y is in the orthogonal complement of W, y must be orthogonal to every vector in W. So that must mean that if you take y and you take the inner product of y with itself, because y is in the orthogonal complement of W, it means it must be orthogonal to y. So therefore, the dot product or the inner product of y with itself, that has to be 0. Okay, but that implies that what is this term? What's that term equal to? Remember, by definition, that is the square root of y's norm. Must be 0, and from there you can easily see that the norm of y must be 0. Now we know the norm of a vector is 0 if and only if the vector itself is the 0 vector. Okay, so therefore y must be the 0 vector. So the intersection between W and its orthogonal complement must be only the 0 vector. Right, the next theorem here is if W is a subspace of a finite dimensional inner product space V, then the orthogonal complement of W, the orthogonal complement of the orthogonal complement of W, which is that there, is in fact W. Now we actually did look at an outline of this proof when it came to the dot product in chapter, I think it was chapter 4. We did look at this briefly, but we will look at this in detail a little bit later in chapter 6. Right, so moving on, we've got these two final examples here with regards to the orthogonal complement. Here they ask us, find a basis for the orthogonal complement of the subspace in R3 spanned by these two vectors here. Right, so what is the space spanned by those two vectors there? So basically you can see W as the span of these vectors. So it's all linear combinations of V1 and V2. Okay, so what is it that I want to find? Okay, I want to find all vectors W1, W2, and W with component W1, W2, and W3. So what I want to do is I want to find all vectors such that W's inner product with V1 is 0, and W also needs to be orthogonal to the second vector V2. Now remember, we did a result which said that a vector is an orthogonal complement of W if and only if it is orthogonal to every one of the basis vectors. Now remember, we said that W is the span. It's this pretty much all linear combinations of V1 and V2. So to find the orthogonal complement of W, we need to find all the vectors pretty much. The only way a vector can be an orthogonal complement of W is if it's orthogonal to both these two vectors. So you want to pretty much go and find all vectors W that are orthogonal to both V1 and V2. Right, now recall that the vectors V1 and V2 were respectively 3, 0, 1, -1, -2, and -2. Okay, now what you want to do is the inner product here is the standard dot product. So what you're going to do is you're going to look at the null space of the matrix, and the matrix that you form is you make the rows of the matrix the vectors V1 and V2. Okay, so there we've got our rows, and you want that to be the 0 vector. Right, so getting the basis for the null space of this this particular matrix here is a straightforward procedure. Okay, then you take your matrix and basically that reduces to and then that reduces to alright, so basically the general solution so knowing what that matrix is there, you can basically let W3 be T, and then basically W2 is pretty much going to become and W1 is going to be minus a third T. Alright, so the basis is going to come that set, and again that just your vector is going to be minus a third, minus 5 over 6, and 1. Okay, so basically your vector is going to be that vector there. Right, so next up we've got this example here. Now the space is given as M22 and the inner product is defined as this one that we have, this trace inner product. And we're asked to determine a basis for the orthogonal complement of W, where W is the span of these two vectors here. So how do we find a basis for the orthogonal complement of W? A vector is in the orthogonal complement of W if and only if it is orthogonal to both these two basis vectors. So again, you need to find vectors that are orthogonal to both the two basis vectors under this inner product. Right, so what we're going to start off with is we're going to define U and V as the two vectors in M22, And let's just go and look at what the inner product of u and v look like. Right, so the inner product of u and v is the trace of the matrix that I get by taking the transpose of u and multiplying that with v. Okay, so you take the trace of the matrix U and you multiply that with the matrix V, and you look at the trace of that. The trace is the sum of the diagonal entries, so we just need to work out the diagonal entries of the product between these two matrices and sum them together. Right, so what's the sum of the diagonal entries? Is you first multiply the first row with the first column, and you sum the two together. That's the entry in the first row in the first column, so it's u11 v11 plus u21 v21. Okay, and then the entry in the second row in the second column, take the second column and multiply that with a second. Take the second row and multiply that with a second column, and you get this term here. Okay, so that is what the inner product of u and v is going to look like. So now knowing that, we now need to find the orthogonal complement of w. I want to go and find all vectors u such that the inner product of u with this first one of the basis vectors is equal to 0, but we found a general expression of this inner product, right? And we remember that is equal to, remember that expression that we worked out there. Let's just keep that in mind. Okay, that's going to be equal to that, because here, what is v11? v11 is 1. What is v21? It is 0. And what is v12? It's 0. And what is v22? It's 0 there. Okay, so that is pretty much going to be the term u11. Okay, now we've got one other basis vector to consider. So there's my second basis vector, and what is that going to look like? Right, that's going to be equal to that, because what is v11? v11 is 1, there's 1, okay. What is v21? v21 is 0. What is v12? v12 is 1. And what is v22? v22 is 0 there. Okay, so that is going to become u11 plus u12. And what you want is, we want to find all vectors u such that u is orthogonal to that vector. Okay, so basically, what exactly is it that I need here? What we need is, we need that to be 0. And we also need that to be 0. So the matrix U needs to satisfy it the following. It's the entry in the first row and the first column needs to be 0, and the sum of the entries in the first row and the first column together with that needs to be 0. Okay, so basically what does that mean? We already know u11 has to be 0. And so that is going to imply that u12 is also equal to 0. Right, so basically the vector, for it to be orthogonal, it has to have these two entries equal to 0. So for u to be orthogonal to both the basis vectors, u has to have that property. Right, so what is a basis for the set of all vectors of the form that have the same form as this. Right, so we can basically write that as U21 multiplied by the matrix plus U22 multiplied by the matrix 0, 0, 0, 1. Okay, so the basis is going to become, right, now note we can make U21 and U22 arbitrary parameters. Right, so the orthogonal complement of W is going to be the span of the following two vectors. Right, there's my first basis vector. Right, there's my second basis vector. Okay, so there's my basis. That is my basis for the orthogonal complement.